Yeah, so let's go into Q&A, and if you guys want, we could go until 5. We can go until just the top of the hour, depending on how things go. But I would say let me give you the usual line here. It is Alt Y on Windows, sorry, Option Y on Mac or Alt Y on Windows. And you guys can type those into chat. And again, we have kind of a discussion in chat, but it doesn't look like there's any questions there. So okay, let me go to Aiden Schaefer first. Sir?
Yeah, you can hear me now?
Yep.
Yeah.
It brings to mind the Stellarator in Germany. It's where they were working on changing the coils on the toroidal machine. So it was focusing and following the waveform as it goes through. Your device is very intriguing. And it's too platonic, they're perfect circles in a perfect tube, which, that gives you some efficiency. But I think when we're working in these fluids, you've got to look at the curl and divergence in the fluids. Maybe like Schauberger has some equations, or what is it? No, it's the Reynolds number of the fluid that you're creating.
I 100% agree with you. Those models are platonic simply because my 3D modeling skills are definitely lacking. But yeah, and that actually brings up a really good point, because there is right here, you can see in this demonstration
share screen.
Oh, thank you. My bad. So this is like, they have the tube moving and they're recording the fluid, and the bubbles are there so you can see how the fluid's moving. So you can already very much see that, what did they name that tokamak? They had the Stellarator.
The Stellarator,
you can kind of see that shape in there. You can see that helix.
Yeah, it's faint, but I've been looking into plasma physics on the sun for a while, so there is a ribbon going through it.
And then
it's probably, yeah, you're on it. You're on the right stuff.
Here's another one where you've got this it's a thin cavity that they're gonna push water over this round object. And so you can see that the round object, when the flow is sufficient, you get
there
this.
It is.
Yeah. So it's like, there's my baby right there. I want to put that in the jar essentially and cavitate that vortex ring. So there might need to be like perturbations on the inside of the glass, such as this, or a twist to the glass. But thankfully, especially where I live, there's a lot of talented glass blowers.
Yeah, there's somebody on Instagram that I've been he makes plasma bombs. So he's good with getting plasma into a couple different glass shapes and such. But yeah, Nerd Glass, I think is his. I'm not going to give out his real life name, but Nerd Glass. I look for plasma bombs, and I've been trying to talk with him, or not trying, but actually just shared this video with him via Instagram.
So in our open session, I want to hear, Aiden, I want to hear more about a plasma bong, because
neon. It's all neon, Tim.
I'm just saying, I have seen the future, and it has the word plasma bong.
Right. But no, I mean, getting the coils in the glass. So I went into Instagram looking for people who are doing plasma art. There's another one like Aurora Sculptures. Look into his Instagram. It's really cool. This Nerd Glass individual said to check him out as well. But so okay, that was my question. You'd looked into the Stellarator, and nice to meet you, Joseph.
Nice to meet you as well. Yeah, there's a lot of work in front of me on this one. This is kind of, I'm at that point where I've got the idea, got the vision. I've seen that, it's a physically real thing. So the next, part's just going to be to try to build one, which, as you will, yeah, I'm probably going to have some weird shaped glass, and you know, probably a different coil configuration. You know, it just depends. But I'm gonna start square one probably with some, you know, one that's more platonic and then go from there, right? I mean, simulations would be great if anyone can simulate fluids in a closed system getting affected by electromagnets.
Yeah, that's
That
that
would
very
be-
expensive COMSOL software
Yeah.
again.
Yeah.
That's where it's at. They know how to do this stuff for sure.
Okay, well, so let me go to Michael Boyd next. Aiden, thank you again, sir. Michael?
So I'm curious, why wouldn't this work in the atmosphere?
I don't know. I mean, I guess you could make, well, I mean, for me, I guess there's a lot of emphasis on sound. And so, you know, sound moving through a denser medium, and then also kind of this like fluid gas or fluid vacuum interface. That's really my biggest interest is, you know, if you have a fluid gas interface, I mean, I'm sorry, fluid vacuum interface, either or, but I'm really mostly interested in if we've got, you know, if we can try to do a vacuum bubble. But, you know, you're like, you're essentially physically, you know, you're putting work on this bubble and it's just a piece of vacuum. And so the sound
Well, I mean,
moving
it's
through the
not
fluid.
just a piece of vacuum, it's a bunch of phonons.
Yes.
It's like you're making like well, phonons are just protons. So I mean, they're mobile. So in the certain, so the question is,
Oh, I see what you mean. Kind of like when they do it with when they put the little styrofoam balls in the acoustic traps.
yeah,
You're
like,
saying like, why couldn't we use the sound to set that up like just with like in
well,
the
I mean, you know what an elf is? It's a
Yeah.
type of lightning called an elf.
Yeah.
And it's a positive lightning. It's positive. It's going towards outer space.
Okay.
And it looks like a ring.
I thought that was Sprite.
Okay.
That's Sprites, right?
That's no, a sprite. An elf is the ring,
Oh,
Okay.
and
That's
that
very interesting.
and so my hypothesis would be that if you can do it in a fluid and you can do it in the atmosphere, well, then you can do it in something that's solid too. So it's a way
Solid would be cool. Yeah.
it's a transport mechanism. So basically, it's kind of like when you're doing quantum tunneling, right? And you're going through this barrier, a physical barrier, which when they first learned about it was the diode junction, thing called a Schottky diode. Okay, and it's just a piece of metal on a semiconductor, essentially, is what it is. And so basically, if you can go through that, if you can do that with a liquid and there's no reason you couldn't do it with a solid too. And perhaps this is the key to teleportation. Basically, you got to create a state where the matter isn't interacting with the vacuum. You follow? And then you can pop it in here and pop it out there. You follow?
Yeah.
It all has to do with resonance and phonons and photons.
It really does. Yeah. Definitely.
So cool. Yeah, I think that I think that's pretty cool. And I've actually seen I've not seen any of the rings, but maybe it could be a piece of a ring where they had to like this experiment in the synchrotron generator where in the vacuum, these little bubbles, I mean, they were like 100 micrometers across. They'd actually show up on the imager, the electron microscope imager, basically is what it is. So, yeah, I think it's something pretty cool.
Yeah.
I appreciate your
definitely merits some investigation for sure.
Yeah, thank you for your presentation.
awesome. Awesome. Michael, thank you as well, sir. Let me go to Jared next. Jared?
Hey, awesome presentation. I freaking love sonoluminescent stuff. So this was super big treat.
Okay.
Couple of questions for you on it. Just the geometry differences. So if you have a cavitating sphere versus a cavitating toroid, right? That cavitating toroid, as its diameter is shrinking, I want to say at the same time its other diameter is shrinking as well, right? So you're getting a different form of compression, right? With a
No, I totally
cavitating
see where
toroid.
you're coming from. Yeah, because you
Right.
know, obviously the math on that sphere, right? When that sphere is cavitating, the math gets intense, the energies get hot, the speeds become fast. You know, I do ponder that. But it's one of those things where, you know, we don't even know, you know, like we need to try it, right? I mean, I guess that's the thing, right? I mean, like worst case scenario is, you know, we get this thing going and we try to cavitate it and it's just like impossible. It just destroys the bubble ring and there's nothing there. I mean, that's a very, you know, that's a possibility. But I'm just curious. It's just something that I want to do. But we saw how stable they were too. So like, you know, part of me is like, maybe, you know, it's really, I just, you know, kind of throwing my money on nature. I'm like, well, I just see there's something going on here. And I know that stuff gets even better when we put it in closed loops. So, you know, that's pretty much the general concept, right? So yeah, I have no idea, but yeah, I've thought about that where it's not going to be that energetic slap that, you know, that we're looking for.
I got another thing for you.
Alright.
So you mentioned it briefly when you said that they got the really high temperatures. They were using mercury. So there's another way that you can get this luminescence with, instead of doing the sound, it's called magnetophotoluminescence. Have you looked into that at all?
No, I haven't. I'll write it down though.
So with that, it's the surface charges on the inside or outside. I want to say it's on both, right? As those surface charges compress, you're and I want to say they're spinning too. Don't quote me. It's been a long time since I looked at magnetophotoluminescence, but the gist is that you can derive these photons from the charges as they're squeezing and compressing with a twist, with an extra motion, because that's how you get your magnetism, right? You have to have some kind of magnetic or metallic surface that these are on, right? So that they have much higher surface charge. So water doesn't have much surface charge that it can hold, right? Mercury has like the highest surface charge that you can hold. Also, the size of your droplet matters, or the size of your bubble matters. So if you have a super large bubble that you're collapsing, you have a lot of charge, but it's going to hit that threshold much sooner. If you have micro bubbles of a couple hundred microns across it, and you are cavitating itty bitty tiny bubbles, you can create frequencies that are way higher in these chirps that you're getting as it's collapsing.
That's
yeah.
a cool idea. Yeah, like, you know, if there is something here and it's to the point of fine tuning, can you actually utilize those super high frequencies you're creating by timing them right?
So from what I've researched, it looks like they have done this decades ago as a means of producing X-rays.
Yep.
There was Julian Schwinger came up with a great, you know, Casimir-ish method of describing sonoluminescence. And then Friedrich Winterberg took that and expounded upon it and said, yeah, let's flip that on its head and let's do that backwards. So rather than compressing, let's explode. I put a link to Winterberg's paper in the chat. If you ever want to take a chance to look at that, it's not very long. It's like 11 pages long or less. It's only been cited like 9 times since then. But those two people, I really like going off of researchers and, you know, see the big hitters. What are they interested in? What are their insights on it, right? And when they started talking about sonoluminescence, that's when I really started paying attention to it.
Yeah, I just think, you know, I don't know how, I definitely don't have the answers. I just feel that this is our mechanism to couple to that, to the vacuum, or to you know, the fields that that everything come from, you know, because all that matters is just a field really too. So once we figure out a couple to the, you know, these fields, or you know, the field in a meaningful way, then I mean, we pretty much got our, you know, then we got it, you know.
That's what Winterberg was saying, was that this is a way of extracting energy from the 0 point.
Yeah, there's, you know, it's just crazy because yeah, the kitchen sink, you know, it's like it captivates your imagination and interest, still unknown. And that actually reminds me of a little snippet from a paper I'm just going to show you here. But these guys were like, they wanted to look at like, you know, is it a quantum effect, right? And you know, I really don't know what a Poisson statistics is, but essentially in there, what they conclude is that the quality of the light coming out of the bubble flashes has this like statistics to it that like show that essentially, you know, it's one of the things that prove that this is a quantum effect, and that they say that if they had to put their money on it, it would be the dynamic Casimir effect. And so that's really where I think the bread and butter of this whole topic is that, you know, vacuum bubbles and sound and coupling to wherever, you know, coupling to a significant field to do what we want to do, which is fly through space really fast. Or-
One further thing specifically on that. So using the metal instead of the like water, with the water, you could just put in a pulse of laser light whose wavelength is equivalent to that minimum diameter at which it hits, right?
Yeah.
But the cool thing is that when you switch over to metal, you can start using RF. You can use radio pulses, and you can tune those.
Shit.
Yeah.
Oh, I mean, sorry. You're right.
So you can actually alter the rate of the cavitation, not just alter it, but all of this always comes down
That's
to
a
fusion of
good
some
idea.
regard.
And that's just another example to throw on the list of how many things you could throw in this thing. So in that case, we'd probably have liquid mercury as the fluid. And if, you know, if we have a bubble, you know, let's say we're doing a vapor bubble, so it'll be mercury vapor in there with a slight vacuum. Okay. And then you're saying we just throw RF on that, and the body of mercury itself is what's essentially vibrating at that point. Will that give us actual mechanical waves into that vacuum bubble? Or
your goal is to get the standing wave at that minimum size to get as much energy extracted from the vacuum as possible, right? So that means that the more energy you can get, the more closer you can get to vacuum breakdown you can get, the more extraction from the vacuum you're going to get. If you go one step further and really put on your mad scientist hat and use radioactive mercury with beta decay, now when you squeeze it down, you hit it with that radio frequency, the chance of getting a beta decay goes way up. So now you get a crap ton of positrons coming out all over the place inside this very confined space, right? And so now you're compressing antimatter. I'm spitballing the mad scientist stuff here.
Yeah, no, I mean, those are the kind of thoughts, you know, that's what got me to this point where I'm like, I need to put a sign on the trailhead, you know, like that's what this is, you know. It's just a whole nother avenue, you know. I've just noticed we have all these different avenues when it comes to how are we going to actually figure out and engineer this, you know, these new kinds of propulsion things. So, you know, very much open to suggestion, very much open to help and resources. If I could network here, you know.
Awesome stuff. Thank you, Justin.
Thank you.
Good deal. Okay, thank you, sir. Let me go to Bill Alec next. Bill, go for it.
Yeah, Joseph, very interesting discussion here. In regards to mercury, they're generally found in fluorescent tubes, is my understanding here. And there appears to be a negative resistance effect. You know, when you turn on a fluorescent tube, and maybe there's something to work with there. The other thing is that it seems to me that in the bubbles, there's a gas, and that gas is what's called Brown's gas. Okay, I don't know if you ever heard of these Brown's gas generators, but what's very interesting about Brown's gas is that, first of all, it burns at a very low temperature. I think it's like 130 degrees C or something. It's like an endothermic process where the gas ignites. You form the gas from water, okay? And it's like another form of water that's not really understood in mainstream science at all. You generally find it at these alternative energy conferences, okay? But the gas, it's called Brown's gas, and it's like another, it's not water vapor, it's another form of water that's in a gas form, but when it collapses, is extremely energetic, okay? Extremely energetic. And the reaction is more electrical than it is, just burning water and, hydrogen and all that other stuff there. But the energetic reaction, it's strong enough to melt tungsten, is what I heard. Okay, it's a gas or a water form in the bubble, and this is what's it self ignites, and it forms this extremely energetic form. So it's something that maybe you would want to look into, but the only place that I know of is in alternative energy, places like maybe what we're doing, okay? But I don't think you'll find it in mainstream science at all.
Well, I'll definitely check it out. Make a note of that.
Awesome. Okay, and let's go to Harold Tabarez next. And we've about 5 minutes left. So do you want to wrap up the Q&A at 5 on the top of the hour?
Yeah.
Okay, and then we can go to Mark after that. So Harold, go for it, sir. We got 5 minutes left.
My question is very short and very simple. One subject of interest is the cavitation in a ferrofluid. Suppose that you're able to create a bubble in a ferrofluid, and you have all your magnetic field inside there. I wonder, is it possible that when you have that perfect sphere or a space that is full of nothing, let's say a vacuum in there, and you pump it with radio frequency, the old saying that for guy who said that you can pump the vacuum with an electric field and you can get new particles to form. Would that create a controllable environment inside that bubble using ferrofluid, in which you have that perfect vacuum in there, pumping with the radio frequency, that it might create like the hypothetical space to create new particles, let's say having a perfect value? Would that be possible to do it in that cavitation model that you are using?
Well, I actually can't say I'm sure. I mean, anything could really happen, I guess. It just needs to be tested. The vacuum side of things, it usually relates to, the dynamical vacuum. And so, if everything is in this vacuum, or if everything is just a field, right, in vacuum, then Oh, man, I guess. What was your question again?
Okay, you describe cavitation, you
Mhm.
know. My question is, can you create a cavitation model to rephrase my
Oh,
question
to
in a
elicit new
ferrofluid?
particles, to elicit new particles, that's right.
Mhm.
Well, I mean, you know, it just depends. Like I said, if everything is a field in a vacuum and you've got a device that you can couple in a meaningful way to these fields, right? That's how we get work done. You know, so we just need to look at, you know, I just think sound is not being looked at enough, you know, just in general. There's this trick up sound sleeve that humanity hasn't realized yet. And you know, I find it highly suspicious that that is our chosen analogy for gravitational waves in space-time.
All right, well, thank you. It was a hypothetical question. I thought you might be able to throw something good, but that's a good answer. Thank you. Great presentation.
Thank you.
Perfect. And Harold, thank you as well, sir. Okay, well, so that brings us, we're just about at the top of the hour. So I'm going to put this thing on gallery view. Everyone, please, again, a big hand for Mr. Joseph Whiting.
Thank you.
Thank you. Thank you for the in-depth presentation. Thank you for the Q&A. You know, you went through it quickly, but there was still a lot of meat on the bone there. And I appreciate you sharing it
I
all.
was worried I wouldn't have enough time. And then I glanced down and was like, oh no, I'm going way too fast, but you know.